Hi folks, and welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to calculate an arc length for a curve written in parametric form. So what we're looking at here is the curve defined by x equals t cubed and y equals 3/2 t squared. We're going to look on the interval 0 to square root of 3 over t. Now, first of all, let's talk a little bit about, what does this curve look like? Well, I can at least get a sense for what it looks like. If I solve this for t, it would be x to the 1/3. If we then take that and plug that there, we're going to get the function between y and x is going to look like something x to the 2/3 power. Important thing to realize is that function's getting bigger as x gets bigger, and it's positive for all values of x in that region. So I'm going to start this with a quick sketch. Now, it's not important that your sketch be perfect, but it is important that your sketch takes into account things like asymptotic behaviors. All right, this function has no asymptotes in this region given, and the effective power is going to be y equals x to the 2/3. This function probably looks, something like this, if I were to graph y as a function of x. There's no asymptotes to consider. We're not doing limit as x goes to infinity or anything like this. So the integral at least is a proper integral with no types of problems. Now, if we're looking for an arc length, the first thing you have to have is an arc length element. So if I were to start by drawing a differential element like this, this has no value for this question. That would be an appropriate element to draw if we're trying to find an area. That's a two-dimensional element. But what we're trying to find is an arc length. We're trying to find the distance along this path out to a certain point. Therefore, our element needs to be an arc length element. So I'm going to start by drawing a one-dimensional element. I'll label it ds, s being kind of a standard variable for arc length. All right, so now the total arc length, call that s, we would get by integrating ds, meaning add them all up as we move along this path. ds, or at least an expression from ds, can be found by Pythagorean theorem, because if I take this little ds and I make this little triangle, that's a dx and that's a dy. Therefore, we can say that ds squared is equal to dx squared plus dy squared. This is kind of the starting point equation-wise for any sort of arc length problem or surface area problem if we're talking about this length revolved about the x-axis. Now, again, the idea here is to integrate the ds term. And there's really three choices here. You could choose to integrate with respect to x, in which case you'd factor a dx squared out of this and square root both sides. Or you can choose to integrate with respect to y, in which case you factor a dy out of this and square root both sides. Or we can choose to integrate with respect to t, our parameterization variable, which is what I'm going to do here because that's what the directions are. So in order to do that, what you do is we're going to take this thing and divide by dt squared. And now, when we solve this for ds, and you would do that by multiplying by dt squared and then square rooting it, you're going to get the square root of dx dt squared plus dy dt squared times dt. An important thing to know is that these are first derivatives squared, not second derivatives. Same thing with this equation here, by the way. This was dt squared. This thing on the left is not d squared t dt squared. If it were, you could not multiply by both sides by dt squared. All right, so in our specific example, what we're going to have is that ds is going to equal the square root of. So now I'm going to glance over and look at my parameterization. dx dt, looking right here, would be 3t squared, and that's squared. So that's going to be 9t to the 4th. I'm going to just double check that. dx dt 3t squared squares to 9t to the fourth. Yep. Plus, okay, now dy dt squared. So I look at my parameterization here. Y is equal to 3/2 t squared. So dy dt is going to be 3t to the first. Squared is going to give us 9t squared. All right, dt. And then I'm going to put my last line, I guess, over to the left here. So the total arc length is going to be, we're going to have to integrate this expression, or infinite sum, 0 to root 3, because my integral is over t, and those are my boundaries on t. Square root of 9t to the fourth plus 9t squared dt. Okay. So the integral is set up. Now I'm going to take a moment here and pause because I just want to chat with the group of people I got here that were with me here watching this, and then I'm going to come back to this. So, folks, so I'm back here, and we talked a little bit about the setup and went over the important things of the setup. Now we're going to talk a little bit about how to work the integral. So now the rest of this video really is going to be about this. How do we evaluate a numerical value for this integral? And you know, standard book ways that calculus texts love to do these things is that corollary to the fundamental theorem of calculus, you know, where integral f dx from a to b is equal to f of b minus f of a, provided that this is the antiderivative of this, or in other words, little f here is the derivative of big F. Now the thing is, that's a pretty big hindrance here. That can be very difficult to do. Lots of functions are very difficult to anti-differentiate. So rather than trying to anti-differentiate this mess, I'm going to go ahead and work this integral numerically, because numerical methods really only have one thing that hinders them. You just need to be able, you know, can you compute a function value everywhere in the region? And the answer to this is yes. There's no asymptotes. There's nothing goofy going on. This thing's defined for all values of t. So what I'm going to do is I'm going to set this up and use Microsoft Excel to integrate this numerically. It's going to take me a moment to do that. I'm going to pause the video while I get the computer ready. All right, folks, I'm back here. So what I've done is I have brought up Microsoft Excel. I've minimized my work for the integral, other than, you know, the only thing we really need here is this integral here. We're going to need to discuss this. So most of the work here is going to be on the right. So the first thing we typically do when we're setting up a numerical integration, or the first thing I do is set up the limits here. So I'm going to start at a equals 0. My upper bound here, b, is square root of 3. Let's see if this will do. Equals 3 to the 0.5. See if that works for me. Okay, there we go. So we're going to integrate this from 0 to 1.732. We then typically choose the number of rectangles we're going to use. I usually call that n. I'm going to go ahead and set this up for 10 rectangles. I'm sorry, usually they're rectangles. Here they're little arc lengths. So I'm going to set this up to do 10 little arc lengths. We're going to need, all right, we're going to need our dt here. So the dt, and I'm going to go ahead and call that delta t in my integral work, because I'm going to use a finite measurable delta t here to estimate the dt. And it's going to equal, just like always, upper bound on t minus lower bound on t, divide by the number of rectangles. So what I'm doing here is setting up a formula here to get me the delta t, 0.1732. Okay. Now I need a way to move through the different elements. So we've got, like, you have to imagine a first element, and then a second element, and then a third element, and so forth. So I'm going to use a dummy variable to do that. I usually call that value I. You can call it k or anything you want. So in my example, I'm going to start at I equals 1, and then 2, and then 3, and so forth. Now when you show Excel a pattern, it will recognize it. I want 10 of these. The next thing I'm going to need now is what I would call my t sub i's. They're the values of t that I need to calculate this function. Now again, hopefully you've seen some of my videos on numerical work here, but I'm going to go ahead and review this just for a moment. So imagine here's one of my elements here. There's a t kind of on the left, there's a t kind of on the right. I like to use the midpoint, whether you're talking about an area or volume calculation. So to get to the midpoint, I'm going to write down the formula here and then just chat about it. This is going to equal I times delta t. Now the product I times delta t, if you think about that, let's say I were 2. That's going to give you 2 delta t. That's going to put you at the right-hand side of the second element. 4 delta t would put you at the right-hand side of the fourth element. I delta t puts you at the right-hand side of the ith element. I want to be in the middle, so what I'm going to do here is subtract 0.5 times delta t, and what that will do is it will put me at the center of the element. Now, hopefully you've seen some of my video work on Microsoft Excel here, but anything that's referenced here has to be locked down. So I'm going to go ahead and hit F4. I'm going to double dollar that guy, and we got to double dollar that guy as well, so that when we scroll, these things get locked down. So if I've set this up right, the very last one should be a little less than 1.73. All right, so we're looking okay. Next thing I'm going to do now is I'm going to calculate function values for this. F of t's and are equal to, parenthesis, okay, 9t to the fourth. So how about 9 times t to the fourth power? Okay, then we need a plus 9t squared plus 9 times t squared. Close my parenthesis. All right, now I've got to deal with that square root. So what I'm going to do is raise that entire mess to the 0.5 power. And there's my function values. They should all be positive. And I'd say they should be decreasing, I believe. Ooh, increasing drastically. I'll take a moment here, pause this. I just want to think about these values, make sure this is working, and I don't want the video to get too long. Okay, so I think that everything's working just fine here. I can check it again before the final results here. But all right, now what I need are these products. The function times dt, and remember what those stood for. Those stood for little arc lengths. So I'm going to call those del s's, or del s sub I guess, for delta s sub I is equal to, and again I'm looking right here, this function times the dt, so that's going to equal this times this, which needs to be double dollared. We don't want that to move. Okay. And now what we want to do is sum those all up. So I'm going to go ahead and do this maybe off to the side. I'll do it right here. So our total value, I'm going to put S sub t here. T stands for total. Total arc length is equal to the sum of all of these products, 3.7. So I think what I'm going to do here is just check this function one more time, make sure I like it, make sure it's working. So 9t to the fourth plus 9t squared. Ooh, I'm glad I checked it, because I wanted to square root that entire thing. As I look at that function, that should be a 0.5, not a 0.3. Glad I looked that over. I had a nagging suspicion. Square root would be 0.5 power. That's okay. Click, drag, right around 7 for our total surface area. My guess is, just a guess here, but if we did find an analytical way to work this integral out, it probably has there's a good chance it has an analytical answer of 7 exactly. That answer is probably good to 4 significant figures. This thing can be integrated, probably a trig substitution. You'll notice you can factor a t squared out of both terms. You can actually factor a 9t squared out of both terms and then square root it. And then you're left with a t squared plus 1. That thing probably can be done by trigonometric substitution, but a lot of arc length integrals and surface area integrals that are generated from these little ds's are very difficult, and numerical methods are definitely the way to go with those. So, hope this video helps demonstrate how to set up arc length integrals and how to work an integral numerically. Have a great day.